We restart. In the lab, we will ask you to use TLS sockets. They are very similar. The good news is it's very similar to TCP sockets with simply an additional step to associate the cryptographic material with the socket. So here is on the client side how we would use a TLS socket instead of TCP socket. So we create a socket, then we transform it into a TLS socket, which means we add to it the ability to encrypt and authenticate. And then, at least in object-oriented languages like Python, we simply use the connect call with a TCP socket that creates the SYN-ACK three-way handshake. With a TLS socket, it creates this plus the handshake that is required for creating the session keys and agreeing on the cryptographic system that is used. So this is all done in one call here. However, on the server side, it's a bit different. On the server side, it starts similarly. We create a socket, we bind it to the local port number, possibly also to IP addresses here. Then we listen. Remember that listen means that I start the listen queue. Oops. Here we are. And accept means I consume one SYN packet and fork a socket. Here, this is what will be done in two steps. So first we fork a socket, and then this forked socket needs to be transformed into a TLS socket. So this is why this is done in two steps. And the creation of this TLS socket causes the handshake that I showed before, how we create the symmetric session keys here. After that, it's very similar to what we had with usual TCP sockets. With, of course, perhaps one difference in terms of performance. Now, if I connect to a web server, probably, hopefully, I will be using TLS. How many round trip time do I need to pay before being able to send my request to the web server? If I use TLS 1.3 and TCP. I close the poll. The majority says C, well, which is not exactly true. Well, in fact, I'm just saying how many RTTs, which is perhaps a very vague way of measuring the round trip time. In fact, we will need all of this to happen. So 5 messages. So 5 messages, that's not 3 round trip time. It's also not 2, it's closer to 2. So correct answer is probably 2. But the truth is we will need to open the TCP connection, at least if we don't use TFO. And then we will need also to have at least one handshake in order to open the TLS connection. So that's very optimized. This is TLS 1.2 had more messages here. So you didn't have just one handshake, but more. But the minimum time, if the time between those two messages is very fast, which is approximately true, you still need to encrypt with asymmetric cryptography, so it might take some time, at least here on this side. But certainly you need at least 2 round-trip times here before communication starts. So if you're communicating with a server, the round-trip time is 100 milliseconds. If you send before receiving 1 byte of information, you wait for 2 round-trip times, which is one of the issues for large data centers in the internet today. A bit later at the end of the course, we will discuss optimizations with application level frameworks called QUIC that try to mitigate this. We have seen one already with TFO, the fast open option of TCP, which will try to save this thing here. Here we've seen that when Lisa receives the certificate from the bank, she will verify it with the CA's public key here, right? What do you think should be in this information that's received from the bank, which is called a certificate here? What do you think that should be received and used by Lisa's software here? I close the poll. The majority says D, which is the correct answer. We need the public key. We need also the identity, something that allows us to verify that what we will check from the certificate corresponds to what is given here. So for example, for commercial entities, it is their name. And then those two together, written in a certificate, will be verified by Lisa using some way of verifying the authenticity of this certificate. So this certificate must have been signed using a private key of some entity, which is called a certification authority. And Lisa will verify it with the public key of the certification authority. But if the public key is in the certificate, of course, this is called a self-signed certificate. It doesn't prove anything, right? It's like when a child signs to the school an excuse for being sick, it's signed by the child and it doesn't carry any weight. So it's the same thing here. Sometimes it exists, it's called a self-signed certificate, but well-behaved browsers should refuse that. So you don't want to get the authentication information from the bank or somebody who pretends to be the bank, because of course the system breaks if that's the case. Which means that you need to be very careful about the software that you use. There is always a bootstrap problem with security. Security always assumes that something that you have in your hand is secure and you have no way to verify this hypothesis. So when you buy a computer, you install an operating system. Where do you get this operating system from? Where, if you get it, typically something installed by the manufacturer of the computer, and that comes with certificates of certification authorities, for example. This is why, of course, you have to be very careful how you install a browser that could be bogus, for example. Voilà. We will conclude with one theoretical question. This is practically less relevant, but perhaps important to understand why things are the way they are. We have seen how TCP repairs losses, but we now discuss why this is so and why sometimes it is not the same here. I mean, we've seen that packet losses occur, and there are two ways that exist in computer networks of repairing losses, more than two, but we can classify them in end-to-end. This is what TCP does. So in reality, when a packet is sent from A to B, there is the source and the destination, but there are intermediate systems, routers, bridges. So those routers and bridges, they also see the packets. We've seen that a NAT looks at the port number. It could also look at the sequence number, and it could decide that if a packet is lost, it sends it back. So this is what could be done if we use what is called hop by hop. This is typically not what is done with TCP. We know TCP goes on the left here. But you could imagine doing here, for example, what is called a TCP proxy. In fact, that is done typically by operators like Swisscom on the mobile network. They will sometimes, or they will often, put a TCP proxy for reasons that will become apparent when we study congestion control in particular, that will open, in fact, all your TCP connections and look inside, and if they detect that the packet is lost on the wireless link between you and the base station, they will retransmit it, because this is where many of the losses occur, and if you repair them locally, you repair at least more quickly. So think global and act local. It might be a good idea to repair the trouble at the place where it is caused, rather than end-to-end. Here, a packet is lost here between you and the base station. You connect a server at the other end of the world, but you wait until an acknowledgement comes or doesn't come from the other end of the world to detect that the loss occurs. So both exist, both are done in practice, hop by hop or end-to-end. And the question is, why should we do one or the other? Well, the internet, in principle, is called a TCP-IP architecture, so it does TCP. The internet philosophy is, no, you should do end-to-end, not hop by hop. Why did the internet decide this? Why in the 70s, the internet, and before it, the Cyclades network in France of Louis Pouzin, why did they decide that? Well, we've seen a reason for that. We don't want to do store and forward, we want to do packet switching. That was one of the reasons. But there is another reason here that is perhaps apparent. Which is, at least in the original internet, that it is not sure that all packets of a given flow will follow the same path. So if that's the case here, R2 may have the impression that packet 4 is missing, but that's not true. It's simply going another way. So it might be impossible or not consistent with the design of a connectionless network layer like IP is, to require that the intermediate systems see the thing that are missing. So that was the reason for that. But we will see that there is another reason for doing the other way around, which is why companies like cellular telephony, cellular operators do some hop-by-hop loss recovery. So for that, a bit of theory. If we consider a channel with bitrate R that loses the probability with that drops packets with certain probability, let's call it P, then we could ask, what is the capacity, in the sense of information theory, of this channel? So the capacity of a channel is an upper bound on how much the most efficient coding system will be able to send information. So it's well known in a wireless network, for example. We know that we've seen the formula in the first week. If I know something about the channel, for example, the signal-to-noise ratio, log of 1 plus signal-to-noise ratio multiplied by the bandwidth will give me the capacity of the channel under a simple hypothesis, which means that any coding system cannot exceed it, and a smart coding system can be very close to it. So we know, for example, on Ethernet cables that are up to 100 meters long, given simple shielded twisted pair cables, the capacity of this is 1 gigabit per second, order of 1 gigabit per second. So you cannot, we can transmit at 1 gigabit per second on those, but if you insist on having 100 meters, you might not be able to do a little more. If we have a channel that loses packets, that loses 5% of the packet, then how much information can we send on this channel? Well, there is a very simple result that says the capacity is the rate discarded by the loss here. So if I have a channel at 1 gigabit per second that loses 1% of the packet, then I could do 99% of 1 gigabit, which is 990 megabit per second of useful information. That's the capacity, which means I cannot do exactly that, but if I'm smart, I can come close to it. In fact, the proof of this result is using something like TCP with an unbounded window. If you retransmit everything that is lost, over the long run, you will reach that capacity here. So that's the first prerequisite. So now, in order to reason and see what is best, is it better to do hop by hop or end-to-end? Let's compute what is the capacity of an end-to-end channel, and I take a toy academic example where I have this sequence of links and assume that the transmission rate is the same and have only one source and one destination. So of course, that's overly simplified. And the loss probability is the same, and the loss events are independent here. Can we compute the capacity of this end-to-end link? Or more exactly, could you guess? What is your best guess for the capacity of this system here? If we do hop by hop error recovery, what capacity will we obtain end-to-end? I close the poll in a few seconds. The majority says A, which is not true. A would be correct if we don't have local repair by hop. It's exactly the opposite. If we do hop by hop error recovery, that means if a packet is lost between R1 and R2, R1 will retransmit it. And same thing, if a packet is lost between R2 and R3, R2 will retransmit it. So we add TCP, if you want, a local TCP between, so R1, R2 are not routers, but they are TCP proxies. If we do this, then the capacity of the link between R1 and R2, by the formula that I said before, is R1 minus P. Now I have a succession of links. I have, well, it's an informal proof I'm giving, but every link has a certain capacity, 990 megabit per second. Then if I daisy chain them, then the total capacity is the mean of the capacity. So the pipes, it's a piping argument, if you want. The capacity of a concatenation is the mean of the capacity of each segment. So we will have this answer. The wrong formula that you gave is, in fact, the formula we would have if you have end-to-end recovery and if the losses are independent. Then the probability that a packet is lost will be given by this formula. And then again, applying this capacity, the capacity is R times this. So that's the capacity we would have if we have the end-to-end. Well, it's interesting to look at the figures when K is large. So 10 hops. 10 hop is large, but not very large here. If the packet loss rate is 5%, which is what you can see on a bad wireless link, then you see that if you do end-to-end recovery versus hop by hop, then you lose 40% of the capacity here. In contrast, if the loss rate is minuscule, which is what you have on Ethernet, or even less here, we see that we are anyhow in the several nines, so it is still better to do end-to-end, but the gain is minuscule. Well, that's the story. That's exactly the story. If the loss rate is large, and it can occur several times, like in a wireless network, then it's a good idea to repair losses locally. If the loss rate is small, it is still a good idea, but it doesn't bring you any significant benefit. So this is what we do in the internet. In the internet, sorry, perhaps I'll do. In the internet, we will do local repair on wireless link with high loss rates. It's done partly on Wi-Fi. We haven't talked about that when we discussed of the Wi-Fi protocol, but one of the aspects of Wi-Fi is that when we send a packet, we wait for an ACK, we wait for CTS, RTS, then we wait for an ACK, and if the ACK does not come, we declare that the packet is lost and we retransmit. So there is a retransmission mechanism at the MAC layer in Wi-Fi, because we expect the error rate to sometimes be large on Wi-Fi. But there is not on Ethernet, because on Ethernet we expect that it's not necessary. So in the internet, the things like TCP do error recovery end-to-end, but they are typically done also on local systems in Wi-Fi or in cellular networks. Voilà, that's all we will see for now on TCP. We'll come back to it. TCP is also the place where congestion control is implemented. And we will also talk about QUIC, which is, at least for Google and sometimes for other companies, is a replacement for TCP. So talk more about that a bit later when we move to the application layer. Voilà. Without any further ado, we move on to the next chapter, which according to the plan is the multicast. Voilà, that will be much shorter, much easier, but you will see in the lab, in lab 3, in the programming lab that we will do, we will be able to play with it. Multicast is something very old, but that is still not very much known, apart from two essential domains of applications. One of them is the original idea of multicast was to replace digital broadcast of TV or radio channels over the internet. That's the model of multicast. And it is used with this purpose. It's also used in industrial applications for subscribe and publish mechanisms where, for example, a device sends data to a multicast address instead of sending to a particular server that is expecting to receive the data. If you don't do that, then when you listen to a radio or a TV channel, for example, the idea of multicast is if you have 1 million people that are receiving the same stream of information, instead of having a huge server farm that's able to handle 1 million video connections, if you could have a way of duplicating the packets along the way, that would be more efficient. That's the idea. More in detail, IP multicast goes with IP multicast addresses. This block, 224, that means from this to that number in IPv4, and that block with IPv6, and we've already seen that IPv6 uses multicast address a lot, locally at least, for example, address allocation, or for the equivalent of address of ARP, address resolution here. So an IP multicast address is the identifier of a group. It's a logical identifier. It's not the address of a certain machine like another normal IP address is. It's a virtual thing that's a group. And if we send, for example, this group here, that means that if a host sends to this group, anybody who's subscribing to the group will receive the information. There are two forms of multicast, any source multicast and single source, source-specific multicast. Any source means that the group is identified by the multicast address. and any source can send to this group, which is the original idea of multicast, but most of the time we prefer to use source-specific multicast, where the group is identified by the combination of the source address and the multicast address here. And only one source can send to this group here, which is what you would like to do if you're listening to a radio channel or watching a video channel, for example. So some of the source-specific multicast addresses are a subset of any source, of the general multicast addresses. Here is a slide that explains quasi everything you need to know about multicast. So I'm showing a source, S, and two potential listeners, A and B, that want to receive the data. And there are multiple routers. We have seen already use of multicast address when, for example, an IPv6 host is trying to acquire its link local address, so it will send a message to everybody using the solicited node multicast address. This is within a local area. Here it's similar, but I assume there are multiple routers. We will see how the routers are involved. So S, A, and B are not in the same subnet here. So S, when it sends to a multicast address, it simply sends. There is nothing special to do. It sends by putting into the packet header the destination address being equal to the multicast address. If nobody listens to the group, then the packet dies. Probably not even with an error message. Now say A wants to receive the data. Then A needs to actively do something. With IPv4, it's called IGMP. With IPv6, it's called MLD, but it's the same thing. It's the group management protocol, or the multicast listener discovery protocol. It means essentially A is saying to the router, I would like to receive the data of this multicast group. And here I'm assuming it's a SSM, source-specific multicast. So A is saying, I want to join this group. Join means as a receiver, as a listener, I want to receive the data. Why would A do that? Well, because an application at A has started some software that knows the address of the group and decides to do that. So it's your Swisscom application, for example, that tunes into a channel here, or your Swisscom box that tunes into a channel. So it will send this message to the router here. Now, when the router receives this information, this triggers the router to operate a multicast routing protocol. That's a special protocol to subscribe, to attract the tree of distribution to this router. So how will we do it? We'll say a few words in a few minutes. So this multicast routing protocol will force R1 to inform R2 and R5 that they need to transfer the data so that it reaches A. And this red block means there's now state information in the router indicating that the tree, the distribution tree, must go through those routers here. The next time when S sends a packet, S is not informed of that. It might be informed because the application informs some application, but at the IP layer, S is not informed. S continues to send, but now the packet is forwarded using the state information in red here, and then it's put on the local area network, where it will receive a multicast MAC address, and this will cause A to receive it. So far, there's only one receiver. It's not very interesting. What happens when hopefully another receiver joins? Hopefully, there are many of those. So there will be, again, the same thing done by R4. The difference is now R4 will contact R2 via the multicast routing protocol, but this will stop here. R2 now already receives the data, so R2 updates is red block, and now R2 has the job. Whenever a packet is received by it, it has to duplicate it. So that's the key thing. R2 now, when it receives this packet, because it has received a join on two interfaces, it knows it has to send the same packet on two interfaces. And the packet will now reach both A and B. The trick is the duplication of packets. Here there are two receivers. It's not S that duplicates, it's the router here. Now, is it a good idea for a router to duplicate, or is it a good idea for a server to duplicate? Well, the jury is still out on this. Still, if you have a sequence of 10 routers and every router duplicates a packet then at the end we have 1,000 packets, right? If you duplicate something 10 times, you have 2 to the power 10, which is 1,024 packets. So that means that every router has done a small job of sending the same packet twice, but at the end we have 1,000 packets. If the source has to do that, the source, whenever it does a send, it needs to do it 1,000 times. So essentially, you distribute the work, but by the exponential growth of the number of packets, there is no single machine that is doing 1,000 packet transmission. You have 10 packets, 10 routers that each is doing 2 packet transmission. So 20 packets, and you've reached 1,000 destination in total instead of having the source do it. So it's good for sources. It puts the work on the routers. It's not too much work for the routers, but it fundamentally changes the nature of a router that now becomes connection-oriented. It is stateful. A router needs to know that this multicast group is active through me. So, and I need to know on which interfaces I need to deliver them. Of course, if S is not a legitimate server of Swisscom, but is an attacker, that's the dream for the attacker. If you want to attack the world and you have multicast, then of course you can do that. This is why multicast is not deployed in the public internet. That doesn't work in the public internet. It works only in controlled environment. It works at EPFL. In the lab, we will use multicast. Multicast is supported by the EPFL network, but you have to be inside the VPN of EPFL to be able to receive those multicast packets here. Similarly, Swisscom, when it sends to you, when you watch a football match, everybody is watching it, so it will be multicast to save the resources of Swisscom, but this works only on the Swisscom network if you're a customer of Swisscom TV. If you're not on Swisscom network, or if you're on Swisscom, you try to receive Sunrise TV, this multicast will not work here. So it will also be confined to a network, which is a very controlled environment where, of course, the operator will filter and will allow only the sources of multicast that are known to the operator. Or in the case of EPFL, we can all do multicast inside EPFL, but this is blocked at the boundary of EPFL. So if a multicast packet comes from the outside, it will not enter the EPFL network. So this is what I said, that the multicast router needs to forward information. Worse, the multicast entries cannot be aggregated, so they are a bit like MAC addresses. We've seen that the very important feature of IP is the ability through longest prefix match to have default routes and therefore to aggregate routes to simplify the packet forwarding. With multicast, it's very difficult to do, which is another reason why it's not deployed on the public internet. At the MAC layer, we have already encountered that, so let's look in detail. In the last leg of the scenario that I showed before, here, this is meant to illustrate a local area network, so a network with bridges, typically, or with Wi-Fi base stations. At the MAC layer, well, things are very different. Originally, remember, the MAC layer was really meant to be a shared medium thing. So on the shared medium thing, in particular, shared medium Ethernet, multicast comes for free. In fact, broadcast is for free. Every packet is in fact broadcast to everybody on a broadcast on the shared medium Ethernet. So this is why on the MAC layer, multicast is very easy. Many applications restrict, in fact, multicast to be done at the MAC layer, iTunes or Miracast. You're able to connect your audio receiver to your TV or to a server. This will typically use multicast, but will be confined to the MAC layer. The MAC layer uses special MAC addresses for multicast. There is one special bit in the MAC address that says it's multicast, so it's one of the bits in the second hexadigit. And then there is a space that is reserved for IPv4, another one for IPv6. And then there are other multicast addresses for other purposes, for protocols other than IPv4 and IPv6. But of course, those are the two main ones we will use. Why it is like this, I'm not sure why. IPv4 uses 24 bits, significant bits, IPv6 32 significant bits here. And for example, if we have an IP destination address that is multicast, the rules say that you take the last 23 bits and put it into the space for those 23 bits, and the other one is put to 0 into this MAC address. So of course you need to translate from decimal to binary or to X, and this gives you this here. So in other words, the mapping from the IP address to the MAC destination address when it's multicast is algorithmic. So we don't need ARP. We don't need to ask what is the MAC address corresponds to this multicast address. It's purely algorithmic. Of course, several multicast addresses may correspond to the same MAC address. We've seen that problem already in another context with solicited node multicast addresses here. But the hope is that within a local area network, that would not have a lot of impact. In reality, many switches do what is explained here. You have two types of switches. You have non-smart switches and smart switches. So if we have a cable Ethernet, a non-smart switch simply treats multicast frames as a broadcast. And this is what also Wi-Fi tends to do. Not all Wi-Fi stations do that, but many would do. Which means what? Which means that if we send a multicast packet because you're watching your football game, then the multicast packet is sent to every device, including your printer, that of course is not watching the football game. But that is what the 30-franc switch that you buy at Migros will do for you. A smart switch, in contrast, will know who is listening and will forward it only to whoever is listening here. But how can a smart switch know who is listening? Well, this is a hack. This violates the TCP-IP architecture because how do I know that B is listening? Well, I know it because B has issued an IGMP or an MLD message saying, I want to join this group. This is an IP layer message. Normally, a switch doesn't look at the IP layer messages, and the 30-franc switch from Migros will not look at it. It looks only at the MAC addresses, does the spanning tree stuff, learns from addresses in the source MAC addresses and so on, but doesn't look at the content. The smart switches, they look at the content, which means that we have a hybrid thing that is using information from layer 3, from the IP layer, to optimize what it does at layer 2, the distribution of packets. Here we start having a collision with the MAC and IP layer, and we see that the legacy that we have of the MAC that comes from the way it was 30 or 40 years ago starts to be a bit inconsistent with how we would like things to be optimally. Here is a Wireshark I did on the solicited node multicast address here. Here I'm sending, so this node is sending a multicast packet to this address because it's trying to acquire it. And if I look at the MAC destination address, I will see this here. Right? How do you think that this was obtained by the system that sent the packet? I close the poll. And the majority says C, which is the correct thing. This is how things are in IP v6. So the IPv6 destination address is this one. So the last 32 bits corresponds to that sequence, which is what will be added to the prefix of the 3333 that will give exactly that. So in IPv6, it's very simple how you go from a destination IP address that is multicast to a MAC address here. We could wonder why we have both. I mean, wouldn't it be better to look directly? Shouldn't the switches simply look at the IP destination address when it's multicast? And that's a valid question to ask. Now, there was one last mystery, that's how multicast routing happens. Multicast routing is a very complex story with lots of different protocols that are very complicated and very smart. But in reality, most systems use only one very simple one, which is called PIM, protocol-independent multicast, sparse mode. It exists in dense mode. I will not talk about it. That's the one that is used typically. Protocol-independent multicast means it's independent of the unicast routing protocol. The topic of the next lectures will be the routing protocol. Typically, it's OSPF in many enterprises today. So the routing protocol is the method by which the routers discover all the network prefixes and how to go there, how they compute the shortest path to go there. PIM exploits that information, whatever the protocol is. There is an alternative to that, which is to modify OSPF so that it also computes multicast routes that will not be protocol independent. So this version is called protocol independent. And the idea is very simple. It uses the reverse path. For example, when a router, such as R1, needs to add the receiver A, remember, A needs to do that to be able to participate in multicast here. So the job of R1 now is to inform all the routers on the path between itself and the source that they should build the distribution tree to send the information back to R1. But that's very simple, at least in the case of SSM, source-specific multicast, because the identity of the group, it contains the source. The source is S, the multicast group is identified by the combination of a source address and a multicast group. So R1 will simply send a PIM-SM protocol towards S, because R1 knows in what is the next hop to R2. It knows it via whatever protocol it uses for unicast routing. So it will send this packet, which is an internal control packet. It's a packet we don't see at the host. If I do Wireshark at S or A, I will not see those packets. To see those packets, I need to log into R2 and do a Wireshark at R2, for example. So this routing protocol packet will be received by R2, and R2 will recursively continue the job by saying, oh, I need to build a tree towards S. How do I go towards S? I go via R5, and eventually it will reach the edge router that is serving S here. This is how it works if we have source-specific multicast. If we don't have source-specific multicast, it's a bit more complicated, and I let you discover that, and it's also a bit less optimal. So this is how things are done very simply. We've mentioned that multicast increases the security, the attack perimeter of any network, which means that if you deploy multicast, you must deploy two things: exhaustive filtering to make sure that you allow only the multicast that is allowed by you. So if you're a Swisscom, for example, and use that for distributing real-time TV channels, then you filter that only such channels are really exercising your multicast protocols. And monitoring. Monitoring means that you observe all the flows that are happening. So all routers do that. They keep record of all the source and destination addresses and port numbers that flow everywhere. And if they see a huge increase in the number of something, there are typically artificial intelligence systems that will try to see whether it's a sign of an attack. So, of course, you will do that. So there's a price to pay for multicast. As I mentioned, multicast is good for sources. This is why you will use it as a replacement of TV distribution over the air, but it makes the system more complex. It's used, I've mentioned, these entertainment networks. It's also used in industrial networks. For example, if you have a sensor that needs to send its information, typically it sends it to, why does a sensor sense information in a smart factory, for example, or in a smart grid? Well, it is because this is used to control other devices. For example, a rotating machine of some kind needs to stop because there is an obstacle on the road. So it's used for control. So there is typically a controller that receives this information. But in a factory or in a smart grid, you also have a lot of monitoring systems to observe what is happening. So the same information needs to be received by multiple devices. So typically in those environments, the sensors will send to well-known multicast addresses, which also simplifies their manufacturing and configuration. You don't need to configure into a device what is the address of the system that it sends to. Last, multicast does not work with TCP. We just finished the module on TCP. Multicast is incompatible with TCP. Why is that? Yes?
Because you don't know who subscribes to your service, you just send it to your address and whoever subscribes receives that.
Because you don't know who is receiving, that's correct. But worse than that, in TCP, there are acknowledgements. So if you're sending with TV to 1 million devices and you would receive 1 million acknowledgements, then of course, that would not work. So it doesn't work with TCP. You need UDP, of course, and smarter error coding mechanism. Typically, you have codes like Reed-Solomon codes that are able, you send parities, you send the data, plus a parity that's able to repair a number of missing packets, whatever missing packet has been sent. This is called also fountain codes that are typically going with multicast. Voilà. And I think that will be all for today and for multicast, at least for the lecture. You will be able to play with it in the lab. Thank you. Enjoy the rest.